an order parameter, the thing that identifies symmetry breaking, to the response. Okay, the fact that you have superfluidity, that things flow without any resistance. How does that come about? Just given this fact. You will see it's a simple consequence. It's not very intuitive, but the mathematics is extremely similar to the way in which solid crystals get rigidity. This is also a form of rigidity, but in quotes, because we're talking about something that flows without any friction. Okay, so so when I first heard about superfluidity, I used to wonder how people figured out helium was a superfluid. Right? They cooled it down, and they, did they do something special? But have all of you seen a video of superfluidity? Anyone has not? Okay, you've got to watch this.
It's like, yes.
Yes, at least one person, maybe out of politeness. But yeah. So I think it really illustrates the importance of having a response in order to identify your Okay, so this is something on YouTube. This is just above the superfluid transition. This thing is really boiling, right? Because it's a liquid, it's in contact with things that are hot, and you drop below the superfluid transition temperature, that's what happens. It's perfectly still. Well, it's still shaking from the original agitation, but there's no boiling anymore. So it's no mystery somebody figured out something happened at this temperature. Right? Something really drastic happens, and let's play it again. Yes, the properties of this material completely changed at this transition. It's really a phase transition, and to actually understand this phenomenon, you can say it's a superfluid. That has to do with how things flow. But how does that relate to the fact that this thing stops boiling? Right. So it turns out once you have a superfluid, you actually have two fluids. You have the superfluid and you have the normal fluid. So you can make waves, you can make excitations which don't change the density. You just convert between these two fluids, and it becomes a really good carrier of heat. Okay, so superfluid helium is an excellent thermal conductor because it has these two different components. They can carry entropy, but they're not scattered by anything else. The mass doesn't change. So that's ultimately the origin of that behavior and many other things that appear, and we'll try to explain them using this picture of broken symmetry, broken continuous symmetry. Okay, so the first part of the course will really be invested in questions like this. And another remarkable thing is the origin of universality. Okay, so we'll talk about systems extremely different. We'll talk about, for example, these ferromagnets. You cool them, they become magnetic at some transition temperature. I just talked about this liquid water phase diagram. Very different between systems. Nevertheless, if you look at certain properties, you don't get hung up on the details, but you look at certain properties. For example, you can ask, as I drop below this transition temperature, how does the magnetization change? Okay, it's going to go to zero. It goes to zero in some continuous fashion. It's called a continuous phase transition. Sounds like an oxymoron. How can it be continuous and a phase transition? But the magnetization dropping to zero is a continuous function, but it's not analytic. Okay? The function is zero beyond this temperature. It rises from here. Something singular is happening. You need to take some derivatives to really expose that singularity in a striking way, but that's really the nature of this transition. Okay? So the magnetization changes, and you can assign an exponent to that. You can assign a number. Magnetization changes as you drop below Tc as some power of the temperature difference. Okay, so those are like the appropriate properties to look at. They're really defined by the very long distance physics of your system. Okay, and that's really where all of this universality applies. There are other exponents you can define. If I apply a small magnetic field, how does the magnetization change, delta? And this is something called susceptibility, again, something related to these kind of properties. And people have either an experiment or numerically or by some means come up with what these numbers are. Okay, so there's some irrational numbers, 0.32, at least we believe they're irrational in 3 dimensions, 4.8, 1.2. And then you go to this completely different system. Okay, you go to this system which is phase diagram of water, for example, or it could be any fluid. We said that there's a transition between water and steam. You go to this critical point. So this critical point is in some ways analogous to this transition. So just orient all your axes along tangent to this phase boundary where it ends, and then define similar properties. Define, for example, the difference in density. Okay, we said the difference in density is going to 0 as you approach this critical point. Delta rho, which is going to be like your magnetization. There's an analog of this susceptibility. If you apply pressure, how much does the volume change? Compressibility. Okay, so you can define analogous quantities. And you find, kind of amazingly, you get the same numbers. Okay, so 2 very different systems. How did that happen? And the answer actually has to do with the fact that you're really exploring a very long distance property of the system. Okay, at long distances, there's a way to think about the physics in terms of the renormalization group. You think about the parameters of the system as you go to larger and larger scales, and then things simplify. Okay, so when you wait for a very long time, go to very large scales, you just get one of a few different behaviors. Either you can, these parameters scale off and go to a point very far away that represents, for example, the magnetized phase, or the other way around, go to the unmagnetized. But then there's this transition point, and the limit again of long distances and small low energies, very little is required to actually specify this. That's why very different systems end up flowing to the same point, and you get these amazing connections between different kinds of physical systems. Okay, and the best description of this critical point, or these kind of long distance properties, is in terms of a field theory. Okay, so that's, for example, where field theory will appear. It's really when you're interested in the longest scales. You're not interested in the lattice scale of what are 2 atoms, 2 spins next to each other doing, but really look at physics at large scales. Things really simplify, and a lot of the details get filtered out. Okay, one of the problems with this approach, of course, is if everything looks the same, you cannot predict details. For example, you cannot predict TC. That's a very important quantity in a magnet. But the very fact that this is so general and universal, it doesn't have anything to say about that particular aspect. Okay, we use other techniques to at least get an approximate understanding of this transition tension. Okay, so it's important to realize the limitations when you can apply this quantum field theory and when you cannot. Okay, so all of these phenomena are really examples where, here I talked about a classical system. You can think about classical statistical mechanics giving you this phase diagram. There's a mapping between that and quantum systems. Okay, we'll talk about this in some detail later, that if you have a quantum system in d spatial dimensions, or rather I should say if you have a classical system in d+1 spatial dimensions, you can map it to a quantum system in 1 lower dimension, at least for all of these low energy physics, the long distance physics. Okay, so there's a mapping that goes that way. You can sort of buy yourself a dimension, and time becomes that extra dimension. Okay, but it gets mapped to a quantum system. So, for example, if you want to study statistical physics in 1 spatial dimension, if you have a model in 1 spatial dimension, it gets mapped to a quantum system in 0 spatial dimensions, just a quantum mechanics. Can we understand quantum mechanics very well? So that allows you to say very quickly, allows you to assess a lot of the long distance physics of 1D StatNet systems. They're not that interesting, basically, because it's mapped to a 0 dimension system. Okay, so you can buy yourself a dimension. Of course, the difficulty is somewhere else. It's quantum or classical, but this mapping helps. And an important question is, does this mapping hold the other way? Okay, so they give you a quantum system in d spatial dimensions. Can I always find a classical system in d+1 dimensions? Okay, so if we can do that, actually it would make life very simple. For example, it will make numerical calculations of ground states very easy because classical physics, classical statistical mechanics is described by Boltzmann weights, right? A bunch of positive non-negative numbers, and you have to sample these different configurations and add them up if you want to find out physical properties. So that's not a trivial problem, but it's a very well-conditioned problem. You're trying to add non-negative numbers, you have some idea about the errors and so on. If you know that certain contributions are small on a scale, you know they're only going to add, so you can bound your results and so on. In quantum mechanics, it's very different. Okay, the key physical ingredient is the quantum mechanical amplitude, which is complex. Different trajectories, if you think about this in the path integral formulation, different trajectories give you different complex numbers. It's not that well conditioned. You may think you're doing pretty well. You have an answer of a certain size, but it may start reducing as you add further contributions. It doesn't happen instantly. Okay, so it turns out some of the most interesting examples of quantum systems are ones that don't have such a map. Okay, there are quantum systems which don't allow you to go that way. Essentially because there's a sort of a dumb way of doing this mapping. If you try to follow that recipe, you find you do get a StatMech system. You get something in one higher dimension, but the weights are not positive. Your Boltzmann weight, which is that's the rule. They're told in StatMech we sum over all configurations. That's the partition function that we're supposed to find. All of these are non-negative numbers, but in quantum mechanics, there is an analogous path integral formulation. You again sum over all configurations. This is sometimes written differently as a path integral. It's essentially some kind of sum. And you integrate the Lagrangian over time to get this weight. Okay, but this is a complex complex number. You can try to rotate this time to an imaginary along the imaginary axis, and that's usually the way in which you go from here to there. So sometimes this quantity, if you look at it closely, under the rotation, it doesn't give you a positive number. Okay, so a simple example is a spin in a magnetic field. Okay, so a quantum spin, a spin and a half that we talked about, our basic building block, that doesn't really have a classical angle. Okay, so if you look at the partition function for a quantum spin, you can certainly write down the quantum partition function. You try to do this change to imaginary time, you find that there are terms which still remain complex, and you don't get a simple problem. Okay, so so there are some problems that are inherently quantum mechanical, and often the most interesting phenomena we know of appear there. Okay, so that will kind of be part 2 of this course. Part 1 you can say is like more is different. That's kind of the slogan that people in condensed matter at least like to say, that when you have many particles, you get phenomena that are not contained in 1 or 2 particles. But here, I think what we are finding out is that quantum systems are really different. This mapping of quantum and classical systems is very extremely useful, but there are cases where it doesn't quite work. Quantum spins, for example, and the quantum Hall effect, we really know of no classical analogs. You get really new and interesting phenomena. Okay, so that will kind of be the second part of this course. Also talk about gauge theories and what's known as topological order. Some of those do have classical analogs, but it kind of makes sense to put them under these. It's very easy for them to violate those conditions. Okay, so to give you an example of this, where this quantum Hall effect, I'm sure many of you have heard about this. It was discovered in 1980. It's kind of an amazing effect. You put electrons in a magnetic field in 2 dimensions, and then you measure, you do the standard measurement, that electrical measurement, measure resistance. Okay, but it's a slightly different kind of resistance you measure over here. Usually apply voltage and look at the current along the direction of the voltage drop. But here you look at it in the perpendicular direction. That's called the Hall voltage. Okay, so the current is running that way, but the voltage is being measured across that way. Okay, the reason this shows up, of course, is because you have a magnetic field and electrons curve in the magnetic field. So you do this at room temperature for most materials, you get some answer, you change parameters, it changes. But for a two-dimensional system, actually one thing you notice, you can, just from dimensions, it turns out the resistance actually has units, the same units as a combination of fundamental constants. Okay, so it has the same units as h over e squared. E is the charge of the electron, h is Planck's constant. Okay, so but when you go to low temperatures under the right conditions, you actually find that it takes on precisely that value up to an integer. Okay, so for n equal to 1, it takes on exactly that value. The Hall resistance is parked at that particular value, and it can only change to be a different integer over here while preserving this coefficient. Okay, so this quantization is quite accurate. It's actually accurate in 1 part in a billion, which is sort of strange given that the material, if you look at actually how they do the experiment, this is not a very clean experiment. Okay, that's what the experimental setup looks like. There's some sample, there are lots of wires coming out. People try to make it as clean as they can, but it's really not that clean. But amazingly, there's some robustness in this phenomenon that actually allows you to get this kind of accuracy. So people use this to define some of these fundamental constants. Now is that accurate? I think in fact the kilogram is now defined in terms of this measurement. It's better than keeping these silicon spheres or whatever in Paris that people used to do before. It's much easier to just measure the Hall effect and relate it eventually to this kilogram. Okay, so in fact, what has changed since 1980 is we are now able to do this at room temperature. Okay, so graphene is a material where if you have a large enough magnetic field comparable to these fields, you can actually see the quantum Hall effect at room temperature. So that's been a huge improvement, and people can easily get a measurement of this resistance by hooking on leads to something at room temperature. Okay, so that's a very robust effect, and that's one of the things we'd like to understand. These are clearly different phases of matter, right? So if you're here, there's a bunch of electrons showing you a quantized number, but then they change to a different quantized number. There's no way to do that smoothly. Okay? So this is one of the invariants we're looking for, one of the things that specifies a phase of matter. Once you know that this has to be an integer multiple of this quantity, if you can prove that at low temperatures, then you really know that these are different phases of matter. That they go from one to the other, and the integers have to be separated by some phase transition. Okay, so this is not one of the symmetry breaking types of distinctions. They have the same symmetry whether you're at n equal to 1 or n equal to 2. Distinction is on some other level, which is very topological. So again, a lot of the second part of the course will be concerned with states of matter that differ at the level of topology. Okay, so it shouldn't be very surprising that topology plays a role in all of these kind of discussions. Topology is really trying to extract the essence of some object, like a shape, for example, the surface, two-dimensional surfaces. You don't really worry about the fine details. You're allowed to make smooth changes. That's kind of our definition of a phase of matter. You're allowed to change parameters. Smooth changes are to be ignored. Right? It's really the drastic changes that we're interested in. Okay, so it's very natural that kind of distinction in mathematics maps onto a distinction between phases of matter. But now we see that there are actually a huge number of such different states of matter, and sometimes they're related to symmetry breaking. So the first thing we'll talk about in this course is the one-dimensional Lassig model. It's literally the simplest many-body quantum system you could think of. Spin one half arranged on a line. We'll see that it has two states of matter. There's one set of variables where the distinction is symmetry breaking. There's a different set where you go to a different set of variables, the distinction is really topological. Okay, so sometimes these things are kind of intertwined in very interesting ways. We like to break it up into part 1, part 2. Part 1 symmetry breaking, part 2 topological phases. But there are deep connections between them, depending on which variables you use. Sometimes that's called duality. If you use the term in kind of a coarse way, but it's really, we are kind of, when you're trying to describe a phenomenon, you're sort of slave to the variables that you use. You have to describe in a certain language, and often there is the real aspects of the phenomenon you want to describe, and there's also the terminology or the variables that you use that comes along for the ride. Somebody else could use a different set of variables, may have a very different description, but ultimately describing the same thing. Okay, so there should be some relation. That's called duality. People think of it as a very deep concept, and it is. If you have to use these languages, then it is a very deep concept. But to some extent, it's also a reflection of the problem with your description. Okay, one description does not capture all aspects of this phenomenon. If you had a description like that, all of these dualities would be kind of tautologies. Right? Saying something that's self-evident in a perfect description of this system. Okay, but we don't have that yet, so we'll make do with what we want. We'll talk about dualities between different quantum field theories, for example, that one of them is going to be this topological and symmetric taking duality. Yeah, and another example that we'll kind of work with in this part 2, just to kind of give you another aspect of this course, which I want to build in, which we'll talk about these very nice theories, but we'll always try to tie it into some experimental system. Okay, so theories that are very beautiful but have no experimental system as of now to kind of elucidate them, we won't really talk about them. But one of the things we'll talk about quite a bit are emergent gauge theories. And systems where there are emergent fermions, so these are examples where you start, like I said, with spins. For example, the spin could be this location of the hydrogen atom in the ice molecules, ultimately the low energy physics is described as something completely different. In fact, this model, it turns out, of ice is a very nice way to get a gauge theory. Okay, so like I said before, there are two positions for the hydrogen. But remember H2O, right? So you're going to have two hydrogens near the oxygen. Okay, so there's a rule that you can put these hydrogens wherever you like, except that every oxygen should have two hydrogens near it. Okay, so you can locally identify a water molecule. So those are called ice rules. Okay, so 2 in, 2 out. You still have a lot of freedom how to do this, especially when you stack it together in a lattice. There's a large number of configurations that's called Pauling entropy. If you look at the entropy of ice at very low temperatures, it's really given just by this counting. Okay, and Pauling first figured that out with sort of a back of the envelope calculation. There were people who measured the entropy of ice at very low temperatures. They did that by just integrating the specific heat. Okay, and we're told there's a third law of thermodynamics which says at 0 temperature, entropy should be 0. They did this integration from high temperature, where the entropy, it's a gas. Then they measure the specific heat and they calculate the entropy. It's not quite 0 for ice. It's 0 for many other materials, but not for ice. And then Pauling came up with this calculation. He did this simple counting, took this constraint at some very kind of simple-minded level, and he was able to reproduce the 0-point entropy that we saw. Of course, the belief is you go to even lower temperatures, eventually that entropy will be released. It will kind of just pick one pattern, for example, or if they're really quantum mechanical, it could do something more interesting. And it turns out one of the interesting things it could do is it could give you an emergent gauge theory. Okay, so this pattern over here, you can think of it as ice, water molecules, but you can also think of it as Gauss law. Okay, so there are these electric dipoles. You can just think of it as a dipole of this proton over here. So the hydrogen is just a proton. So there are dipoles that either point in or point out. And the rule is 2 in and 2 out. That's just like Gauss law. If you think of these as electric fields, 2 electric fields in, 2 out, it's just saying there are no charges inside. Divergence of the electric field is 0. So an effective theory for this is just a vector field, E, which has a divergence-free condition. If you write down the simplest quantum dynamics consistent with that, you get Maxwell electrodynamics. So that's really trying to build in a dynamics which will preserve the divergence-free condition. So you get divergence of E is 0, and the Hamiltonian is some E squared plus B squared. And B is just conjugate in some particular way to the electric field. Okay, so that could be another outcome. In fact, in materials, not ice, but spin analogs of this. They're called spin ions. You have spins that can either point in that direction or that, but there's a constraint that 2 spins have to be in, 2 have to be out. There is some evidence for this kind of gauge theories being realized. Okay, so we'll use that as a motivation to talk about gauge theories, emergent gauge theories, and the physics will be very, we'll take a lot of results from high energy physics. For example, Polyakov has studied these kind of gauge theories back in the day. and we'll use those results, but the setting is very different. Here we really have a lattice. This is not a gauge theory that goes down to, all the way down to Planck scale or something. It's really cut off by a lattice where the degrees of freedom are very obvious. There are no infinities, for example, in these models, at least not from high energies. So it'll be a setting where you can do quantum field theories without, having to worry about infinities. Yet the physics will be very, very similar. Okay, so that's kind of where we're going to end up, hopefully, in this course. Topics like this quantum Hall effect and gauge theory descriptions of things like ice. Okay, but the first thing we'll begin with, like I mentioned before, and I'll have notes put up on the course website, is we'll start with the Ising model, but it's really the quantum Ising model. In one spatial dimension, I read that is 1 plus 1, one space and one time direction. So again, you have spins on a one-dimensional lattice. We'll sometimes call it a chain because it's one-dimensional. Okay, so they can be either up or down, like we said before. The Hamiltonian will make it really simple.